It's recording. All right, sorry for that small delay. This is a meeting packed full, or a day packed full of Zoom meetings, and before this one, Zoom just decided that it was done and needed a fresh start. So, okay, so I was looking through kind of what my original plans were for what we're going to talk about now in this unit, and I just couldn't find the nature inspiration in the original unit that I was kind of wanted to talk about, which had to do with sort of consensus dynamics and we got into sort of parallel numerical processing and stability, and it felt like it was sort of very weakly related to the core kind of subject of the course. And I know I originally put it in there, but I think that now my kind of goals for this course have kind of changed. So I'm skipping the consensus dynamics that originally was kind of, which are also coincidentally sometimes called epidemic models of communication, where nodes on a network bump into each other to share information the same way individuals might bump into each other to share infection. And skip straight to the next unit, which is getting into neural networks, which has much more sort of bio-inspiration. And then that, my goal then was helps us get into things like cellular automata, and which I think some people end up making use of in their final projects, and then gives us more room towards the end of the class to talk about more contemporary stuff in kind of like bio-inspired multi-agent robotics and things like that, which in the end, which I initially only had like one lecture on, and now maybe we can talk about in a little more detail. So I'm throwing out the other stuff, which I think you can get in some other courses that that I don't think really fit well with the bio-inspired AI and optimization, and jumping sort of straight into the neural network stuff. And if it looks like it makes sense to bring them back, then we can bring them back towards the end of the semester. But for now, we'll kind of keep it as bio-inspired, and then see if we can bring them in as advanced topics later, if that makes sense. So neural networks. We don't have a theory. So yeah, and so I'll keep that in mind. So I think I still can potentially bring this stuff back. So the things that I was originally going to be talking about are things like the distributed average consensus problem, and how it as itself looks like a parallel, or how you implement it in viewing it as a parallel numerical algorithm. And so this requires a little bit of linear algebra in order to understand, do things come to consensus, and so on and so forth. And that is interesting to me personally, but it's something that ends up straying a little bit from the kind of bio-inspired roots. So we can always come back to DACP and then talk about how it relates to things that we see in these other sort of bio-inspired stuff, maybe as an alternative framework. But for now, I'm going to sort of like put it on hold, and then see about coming back to it later in the kind of last couple lectures of the semester, as opposed to focusing on it now, because it is such a shift away from things that are directly kind of bio-inspired. So I still leave it on the table to bring it back, but I just was having a hard time kind of connecting it to everything we've been talking about so far. Okay. All right, so I did want to focus, so now the kind of, we're saying, you know, what about these neural networks, which a lot of you have a lot of background in. And so some of this will be a little bit of review. I'm hoping to go into a few fundamentals that maybe you don't see in your standard neural network class, and provide a little bit more of the biological foundations, and then try to also go into a little hairier neural network topologies that that are less popular than some of the feed-forward designs that you see in most of the machine learning literature nowadays. And so a neural network sort of was, you know, a neuron, I guess we could focus on first, is let's look at just neurons. And, you know, you can have these neurons, which I'll draw kind of a cartoon neuron here, where you've got this thing here that, and I'm drawing a vertebrate neuron. An invertebrate neuron looks a little bit different than this, but it has basically all the same components, but it's just shaped a little differently. And an vertebrate neuron, you've got this cell body. So this is an individual cell, and it's got these funny little things coming off of the cell body. Called dendrites. So maybe I'll write that around here. And along with these dendrites, it has this long axon. And this axon is going to have terminals along it, which will terminate onto the dendrites of other neurons. And so you can imagine another one of these cartoon neurons down here. And it's got its own axon. And the places where these axons and dendrites come together allow for the synapses. So these synapses, basically there are junctions between these axons and these dendrites where you can get a transmission of neurotransmitters. So I'm going to call this, you know, neuro transmission. And you basically can think of these tiny little chemicals are going to be moved from the axon to the dendrite. And so you've got from the axon here, you've got these neurotransmitters that end up getting communicated to the dendrite. And this this whole process it is, so when you you know, so when does this happen? Well, this neuron sits at, well, so what you'll get moving down this axon, so you get the transmission of these action potentials, where basically you've got this where the neuron is sort of always sitting at some level here, and then it ends up receiving a signal from another neuron. So we call this a presynaptic neuron. So the neuron that is connecting to its dendrite ends up causing an electrical potential at the neuron, we'll say at the dendrite, to moving above some threshold. And when it moves above that threshold, so we can view this as a stimulus, that triggers a process in the neuron, which causes the neuron to then end up, even though the stimulus might be removed at this instant, the neuron continues to raise an electrical potential. And this is, you know, let's say it starts somewhere over on this side of the neuron, then as it ends up causing its own potential to raise up higher, that it creates a distributed pattern of firings down the neuron, where you get something that looks, so this is over time, you get these little pulses here, which come back down to, this is a resting potential. You get one of these so-called spikes that ends up being transmitted down the axon and end up then being communicated to another neuron via these dendrites. So you probably have all sort of, you know, back in some basic biology course, kind of talked a little bit about this already, is that you have you have a stimulus which can cause a neuron to fire, and that firing causes this information to move down the neuron. And then if the information itself generates a large enough stimulus at another neuron, then that can trigger a similar process in that other neuron. And so you get this kind of communication of information across this network of neurons. And so in a human brain, you can have, just to give an idea of scale, something like 10 to the 11 neurons. And then each neuron could have anywhere from, say, 10 to the third, so 1,000 to 10 to the fourth, to 10,000 connections to other neurons. So a lot of times I think when people picture neural networks, they picture these cartoon diagrams where you've got one neuron connected to 2 or 3 other neurons, when in reality it's a much, much denser connection inside this brain. So it's a very complicated mess. And on top of that, you can actually have neurons connected to themselves. So you can actually have, axons can connect to their own cell body, in which case this is referred to as an autopse. So it's like an auto synapse. So it's a very, very complicated connection structure here. But then, so once you've got all of this topology set up, then each neuron can adjust how much of this neurotransmission, how many of these neurotransmitters are sent into the other neuron. And so basically neurons can adjust their sensitivity. So they can adjust their connection strength. They can adjust how much each neuron affects another neuron. And so that is something that we refer to in the neurological literature as neuroplasticity. And this is the change in, I'll call it synapse sensitivity in response to the environment. Now, if we were to use a more layperson term for neuroplasticity, does somebody else sort of say, like, if I was trying to explain what is neuroplasticity, does somebody else have another description of, like, what do I say? Like when our brain goes through some neuroplasticity, what did our brain just do? What do we call that? Like if you were to talk to a 4th grader, learning, that's what I'm looking for. Yeah, so this is basically a fancy word to say that, it's the capacity for learning, so. And so we think that the mechanism for learning things is a mechanism for neurons changing how sensitive they are to the influence of other neurons. And so this whole process kind of started with this guy, Otto Schmidt. So and as a graduate student, so you can view, I think he was an electrical engineer, but as a graduate student, he worked on squid neurons. And so there are neurons in the squid that are extremely long and extremely thick and easy to work with, especially during the time that Schmidt was working with them. And so Otto Schmidt was sort of one of the first ones to electrically assess how a neuron works, and discovered this pattern where if you give a neuron a little bit of a stimulus, it can then trigger this continued activation for a certain period of time that then creates this sort of chain all the way down the neuron. And so one of the the sort of first bio-inspired adaptations out of this was the so-called Schmitt Trigger. And if you've, for those of you, maybe in a robotics application or an embedded systems that you might have seen Schmitt triggers before. They're sometimes also known as sort of hysteretic triggers. And the idea behind a Schmitt trigger was that if you have some input signal and you've got some output, then the thought is that maybe your input needs to reach a particular threshold. So if your output is low, so your output is down here, if your input finally reaches some threshold here, it will cause your output to go high. But then if the input then goes low again, the output will stay high until the input gets sufficiently low to force a switch back down. And so you end up getting this loop. And this was inspired by this idea that a neuron, if you give it a little bit of a stimulus, it causes it to fire and it will stay activated for a certain period of time, even after you remove that stimulus. And so Schmidt looked at the kind of neurochemical mechanisms for how this worked and built an electrical analog for that. And that became this, known as this Schmitt trigger. And this pattern that I've kind of drawn here, where you need a certain amount of input in order to reach a threshold before you get a firing. And then after that, you need another amount of input to bring it back down, and I'll get to that question again, is known as a hysteresis loop. So I see a question here, why the input goes negative goes in the other direction. So this is just a general input-output map for the innovation that we refer to now as a Schmitt trigger. And so the idea is that if you were to buy a Schmitt trigger like off the shelf, it would have an input coming into it, and the output would be sitting at either a high state or a low state. And so it has kind of a memory, and you can imagine that it rests kind of in this middle state here. And in this middle state, you don't know if the output is going to be high or low, but from this middle state, you need to either, if you want to guarantee that it's high, you're going to have to bring the input sufficiently high, and that'll force it to be high. If you want to guarantee that it's low, you've got to bring the input sufficiently low, and that'll force it to be low. But if you sit in this resting state here, then it gets stuck in its resting state, either up here or down here. And so the idea behind a hysteresis loop is that the output is somehow decoupled from the input, and that you have to force the input over a threshold. And there's two thresholds. There's an upper threshold and a lower threshold, and the output will not switch unless you cross these thresholds. And so there is a history dependence, because it's not enough to know, in order to know the output, it is not enough to know the current value of the input. You have to know the history of the input. So in order to guarantee that the output is high, I have to know that the input previously was sufficiently high and never became sufficiently low. That's the only way I know that it's going to be sufficiently high here. And yes, so magnetization shows hysteresis loops. And this is similar to a flip-flop. That's right. So a flip-flop, if you think of from your computer architecture classes with like some sort of, a flip-flop is a simple D flip-flop. Whatever the input is here, it doesn't really matter. You need the clock to happen. And once the clock happens, it kind of shuttles this around here. And so the flip-flop has memory. And so in order to change the output, you need kind of a clock here. If you think of kind of like what's an even more basic electronic element, you have an RS latch. And an RS latch is kind of like a flip-flop without the clock. And so they were getting kind of more and more into this, this basic phenomena here where it's an asynchronous memory. So the output will hold the output until the input crosses a particular threshold. So again, we can think of this as an asynchronous memory. And in fact, some people take synchronous elements like D flip-flops and they wire up combinatorial logic to the clocks, and that turns them into asynchronous memories as well. So one of the first ones was this Schmitt trigger. And now he wasn't thinking about memory necessarily. He thought the Schmitt trigger is really good for things like debouncing. So you can think of it as like a debounced switch or a debouncing switch. So you might imagine, if you've got a sensor that has an input that is noisy, then so if I were to draw over time, for some reason my stylus got unpaired for a second. All right, good, now we're back. So if I were to draw a noisy, I have a time signal here, and I have some input signal that, let's say it kind of moves up and down, but it has some noise on top of it. And I would like to detect when I cross some threshold, so maybe my threshold is up here, then if I just make the output a direct mapping of the input, then I am going to get a bunch of, I'm only going to get these like 4 points as my output. So I'm going to get a real noisy output. And so the thought was that if I'm worried about these like spiky transits, then if I implement a hysteresis loop, then it kind of waits for my input to get sufficiently high in order for me to switch the output. And so noise won't be enough for me to switch my output. I actually need the whole signal to drive the signal sufficiently high in order to switch the output. And then likewise, if the input signal comes down and it gets close to my threshold, then I don't get chattering anymore. It has to actually come down and go beneath that. So this is a way to prevent chatter. So you can see these Schmitt triggers also implemented in like heating, ventilation, and air conditioning systems. And so as the temperature gets close to a threshold, it might just spontaneously go over that threshold, or maybe there's electronic noise that goes over that threshold, but you don't want to have chatter. You want to kind of commit to the air conditioning being on or the heat being on. You don't want to constantly be switching on and off. And so in between your temperature sensor and your air conditioner, you put one of these hysteresis loops. And this was inspired by looking at this squid neuron initially. So, so that's who we have to kind of thank. But eventually people started realizing that there was more that you could do with these neurons. You could build these networks of them. And that is what left us to sort of start thinking about these artificial neural networks. And so the thought was like, all right, well, if we're trying to think computationally about what these neural networks are doing, other than just filtering noise, how are they actually doing computation? Then how do we build simple models of them? And so we're eventually going to talk a little bit about spiking neural networks, but we're going to sort of first start with the basic model of a neuron where we don't worry about the spiking and we're worried more about the kind of connection topology. And so a basic model of a neuron is this, you've got some inputs, which I'll just call, scalar values, x1, x2, down to xn. And each one of them maybe has a gain that I'll call a weight. And then all of those end up getting summed together. And then that sum, which I could I could even call a vector. So, you know, I could make, I could call this maybe W transpose X. And so then that sum ends up going into a activation function, so to speak, where it just takes that as an argument. So I'll make this W transpose X. And then that produces some scalar output Y. Activation function. And so we can write a simple neuron as Y is equal to F of this weighted sum. And then of course, I also need to add a bias term. And so this is actually has a little bias term here as well. So I didn't write that in initially because a lot of times you just include the bias as a weight. And so this here is our sum that we're passing into this activation function. And so if you like, I can write that whole thing out as just a sum from 1 to n of each weight times each input times a bias. And those of you with a statistical background, you know, should recognize this as the same form as the so-called generalized linear model, or a GLM, where the activation function is related to the so-called link function in a GLM. So I see, does the bias correspond to a threshold that the linear combination of input weights must exceed? Yes, you can definitely, and we'll get to that, but you can view this bias term here or down here as a kind of threshold, similar to that threshold in the neuron case. So in the, if we were, this isn't a spiking neuron, but in that perspective where you view the action potential, where you said that we needed a particular threshold level of input in order to generate the spike, then you also, that bias views that as kind of a threshold that you have to exceed. Right. And so, although this is a fancy way to write a neuron, this basically shows that a neuron is implementing a generalized linear model, at least if we assume that these weights are coming in linearly like that. I see, does it have feedback as well to increase or decrease the weights? We haven't got to that yet, but yeah, that would be the next step, is that how do you end up setting these weights here? And in the setting of those weights, the training of the neural network, that would end up being like fitting weights to a regression here. So that's what I'm trying to get to here, is that a generalized linear model is basically a generalized linear regression. And so if you're not familiar with GLMs, basically GLMs talks about, well, the response variables of the world, the outputs of the world that we would like to fit inputs to, are not necessarily going to be linear combinations of our inputs. But maybe we can find a nonlinear function that if we take those outputs and we map them through that nonlinear function, then the resulting stretched output will end up having a linear relationship to our inputs. And that's kind of the assumption you make when you approach a so-called generalized linear model, is that you are assuming you can find a so-called link function, which takes an output, which might just be a 1 or a 0 output. So like, is it going to rain today? Well, I've got a bunch of different predictors for whether it'll rain today, and my output is it's going to rain or it's not going to rain. Well, there's no way I can map all of my predictors linearly to just 0 or 1, but maybe I can find a nonlinear way to take anything between 0 and 1 and stretch it out over an infinite range from -infinity to infinity. And then that mapping where maybe 0 goes to -infinity and 1 goes to infinity, after I've stretched my output space, then now all of my predictors relate linearly to the problem in this new space. And so that's the role of a link function, is to take a data set that you can't make a linear relationship to and stretch it so that you can make that relationship to. And then so this link function we can then implement in a neural network as a so-called activation function. So we can say y is a decision variable, or xi is dependent upon. Yeah, that's the way you can view this here, is that y is a response variable. So you can view this as a dependent variable. And each of the x's, so I'll say x vector here, is I'll say predictor vector. And so there's a bunch of plausible predictors that are bundled up inside the x vector. And I'm trying to build a statistical model that maps x into y. And so a generalized linear model does that, and so does a single neuron. Okay. So and then with this perspective, then these weights here become regression coefficients. And so if you're training a neuron on a particular task, the process of training is the process of coming up with the best weights. And by best weights, what we mean is the best fit model. So we are fitting a generalized linear model to data. And that is what you're doing when you're training a neural network. If your neural network only has one neuron, you basically are just doing a fit of a GLM to data. And you might have come up with an interesting activation function, but that is equivalent to coming up with an interesting link function. And so there is nothing particularly exciting about a single neuron that goes beyond what statisticians are already doing with generalized linear models. But this is where we're going to start from. So are there questions about this so far? And maybe it'll help if I show this kind of more graphically, which I'll do here in a second for a simple classification problem. Let's see, so the weight Wij corresponds to neural plasticity between neuron I and neuron J. So if neurons were connected together, then you could imagine there would be an additional neuron. We'll call this Z, which is an output from another neuron. And so in that case, this weight W would end up being the kind of sensitivity between the output of neuron Z and whether neuron Y is going to fire. And so as you train the network, as you kind of enhance the synapse between neuron Z and neuron Y, that would be equivalent to increasing the weight, which I've drawn here as W1. So this here is like the, I'll say the sensitivity between neuron Z and, or I'll say neurons Z and Y. Yeah. So right now we're only thinking of a single neuron. So X is just a bunch of predictor variables. But once we have a network of neurons, then each individual neuron's inputs will be outputs from other neurons. Okay. So, what are the types of active? So if I were to ask the statisticians, what are the types of link functions? And they would say, for this type of data, we use this link function. For this type of data, we use this link function, and so on. And then likewise, there are a library of activation functions that you see in neural networks. And so this can get much more complicated. And those of you who do deep learning in your own grad work are going to be familiar with other choices or rectifiers and other sorts of things. I'm just kind of starting with some basics here. And so common activation functions include things like, you have thresholds where you've got f of some vector, and I'll just call this vector x. So you can view this as the weighted combination of all of those inputs is going to be equal to 1 if this x is greater than or equal to 0 and 0 otherwise. So if x is less than 0. You can have linear activation functions. And so a threshold activation function really sounds like you're activating something. But in the strictest sense, again, we want to sort of figure out what's the best activation function for a data set. And sometimes we want to be fitting, we actually have a continuous variable. And so our output that we're trying to fit may not be just 1 or 0. Our output we're trying to fit might be continuously moving. And so in that case, then our activation function might just be linear. And so in that case, we might just have, f of x might just be equal to x. It might just be the identity. We just pass the weighted combination right through. You could have logistic. And so in that case, your f of x might be equal to a sigmoidal function like this one, where it'd be like 1 plus exp minus x. And so again, where x is our weighted combination of inputs. And so that is going to is one particular type of sigmoidal activation function. In this particular case, if x is equal to 0, then the denominator down here, if x is equal to 0, then this exp is going to be equal to 1, and so this becomes 1/2. But if x is equal to infinity, then this goes away, and so then you just get 1/1, so this is equal to 1. So this sigmoid here, implemented like this, might go from 0.5 all the way up to 1. So that is this particular activation function, but you can of course play with the logistic to get it to do other things. And then you can have additional types of sigmoids like the hyperbolic tangent. So a hyperbolic tangent, which is another type of sigmoid where your f of x is equal to 1 minus exp, and let's say minus 2x over 1 plus exp minus 2x, which otherwise is known as the hyperbolic tangent, tan h of x. And so these, like I said, are both sigmoidal. And you can basically view these bottom 3 as ones used in regression problems. And you can view this top one as used for binary classification. So, there's a question of like, what is softmax? So again, we're getting into things that are into the weeds of some sort of deep learning type things that we might talk about a little bit later. But so those of you who are sort of familiar with softmax, is that softmax provides a way of associating probabilities to a number of discrete outcomes and then choosing the one that is sort of most likely. And so I would say softmax is more complicated in that we don't it's coming much more downstream, and it's a much more integrated structure. And so I want to delay that question for now, but it just sort of but the spirit of the question is good. It's sort of, you know, Softmax, which those of you who are familiar with Softmax, provides you a way in which you take latent variables inside a neural network and turn them into something that is perceivable on the outside. And so, so maybe we can get into talking about Softmax in particular once we're kind of ready. But right now, we're still just thinking about a single neuron. And so we've got a bunch of inputs, and we got a single output, and we're, you know, that we're going to say that we're either got a continuous output or an output that is just a binary classifier. So with that in mind, let's then focus on a simple application. So a single layer perceptron. So and I know this will be old news to a lot of you who are already using neural networks in your own work. This is kind of like the basics of this stuff. You may have seen this in machine learning classes, just sort of getting through kind of the basics before we can kind of build up into some other things. And as we get into things like cellular automata, it'll be useful to at least make sure everybody's on the same kind of grounding, because you can view CAs as a specialization of neural networks. And so so that's why I just want to make sure that we're all kind of have the same background here. So a single layer perceptron, maybe I'll put parentheses around single layer there. And so I am going to use this, our activation function is a Heaviside step function, which is the same thing as the threshold function that I mentioned before. And so f of x, or maybe I'll call it x bar, where x bar is our weighted average, and that is just equal to 1 if x bar is greater than or equal to 0 and 0 otherwise. And so in the case of our single neuron, then our f of x bar is just going to be equal to 1 if our this vector w plus our bias is greater or equal to 0, and at 0 if this weighted vector is less than 0. And this is where that threshold comes into play here, because you can kind of view this predicate as asking, well, is this W transpose X greater than, equal to, or less than this negative bias term? And so you can view this bias as a kind of threshold for activation. And so if our, I don't want to use the term yet, but if this vector is similar enough to our input vector, then we will exceed the threshold. And so you can make this bias term negative. And so then you could say if the W vector is similar enough to the X vector, because you can kind of think of this as an inner product, those of you that are more kind of linear algebra or geometrically inclined, you can view this as, or even a cosine, you know, so if the angle between these two is close enough, then is sufficiently close, then we're going to get a firing. And so this threshold, this bias, depends or tells you how close they need to be. And so what do we do with this perceptron example here? And so, and I guess I could also write this as W dot, where you have it. So this is a dot product. So if the dot product of this weight of these weights with our inputs is sufficiently large, then we activate. What can we do with that? And I see a question here. Is that a Z in between the W transpose? Well, yeah, so this is supposed to be like a, I'm going to erase this. Oh, that's a giant eraser. I'm going to erase this and try to make it clearer as I'm saying that's greater than or equal to or less than, and like a question mark there. So what I'm trying to say, it's like, so it wasn't meant to be a Z, it was meant to be greater than or less than. And so have we crossed that threshold? So maybe in this white space down here, then we can kind of think about this. So if I'm plotting, let's say this is in just vectors with in R2. So let's just say that X and W, for example, are in, so this is an example over here. Let's say these two are both in the Cartesian, or in R2. And so if I were to draw that, then I might draw the input vector X as being here. And I might draw my weights, all of my weights, I can represent them as a vector over here. And then we can then view this, if I were to draw then a line perpendicular to this weight vector, then all of the vectors, the X vectors that are in this region above that line are going to give me values where W transpose X, where the dot product of these things is greater than or equal to 0. And so asking, is the dot product of W and X greater than 0, which is what this neuron is asking, is just asking, is the X vector pointing in the same direction as the W vector? So if my neuron has been configured with these weights, then I'm just asking, is my X vector in this half of the plane or that half of the plane? So if the X vector was over here, for example, then for this X vector, then our output would be equal to 0. But for this X vector, our output would be equal to 1. And this is in the case where the bias term is equal to 0. And so as we lift the bias term, so as we move this bias B greater and greater, then what we're going to end up doing is shifting this plane that is perpendicular to the W vector along the W vector. So if I move in, if I maybe draw this a little thicker, then this direction is what happens when we increase, and I guess I should say increase negative B or something like that. But it's the idea that as we increase this threshold, we are going to slide this line along W, so that we are going to then, instead of just simply dividing so we're always going to be dividing the space into one region where it gets y equals to 1, and another region where it gets y equals to 2. But we're kind of now asking, how much of an agreement do X and W have to be in order for us to accept that X vector as being allowed into the y equals 1 space? So yes, a translation. You can view increasing the threshold is equivalent to taking this geometric interpretation of our machine learning problem, and we'll see why it's a machine learning problem in a second, and that and then translating. So increasing that threshold B is the same thing as translating this separating plane along this W vector, this weight vector. And so this W vector is something that I'm now going to start calling a feature vector, where I'm saying that by setting these values of W in this space, we are effectively selecting for features that we like, that we want to find, that we want to classify as good. And this bias term is kind of telling us how much in agreement do we need in our input features with our desired features for us to say that that's good enough for us to move into this y equals 1 space, in order for us to classify this as y equals 1. So to make this a little more concrete, let's set this up as, let's say I do have, so this is a another more concrete example. Let's say I've got these two features that I'm interested in, say car speed and car size. So these are two things I can measure with every car. And I see, yeah, so it's true that X is a vector of features, but I am calling the weight vector a feature vector in this case because I am trying to define which features I care about for this classification, or what combination of features I care about for this classification. And so I am trying to define the elements of the class. And so I'm sort of saying, what does it mean to be in the class? And that gets encoded into the weights of the W vector. So that's kind of what I'm saying here. So like in this particular example, I have car size is something I can measure about the cars. Car speed is something I can measure about cars. But I am not sure, and I'm interested in, say, American cars versus imports. And so I want to know, can I effectively classify cars into whether they're likely an American car or an import based on these two variables together? And so I have some cars that are up here, and I have some cars that are down here. And so visually, I can see that there is a line that is separating these two groups. And so if I could just have my machine learning algorithm find that line, then the weights that define that line end up becoming a function that allow me in the future to take any car speed combined with any car size and then make an estimate on whether that's an American car or an import. So as my example here, let's say these, for example, are American cars, and these ones down here are imports. And so this orange line here defines, it separates the two classes. And so I would like to then find a W that, and I could say also and bias corresponding to this line. So if I were to pick maybe a different color here, so if you were to think about that, then I say, well, okay, so this here might be my W vector, and it is perpendicular to this line, and exactly where the orange line intersects with this vector corresponds to this bias term B. So together, the weight and the bias effectively define the entire line that separates these two. And so we can actually wrap the bias all the way up into the weight vector. So we can view if we kind of think about our neural network as having an input that is always equal to 1. So if I were to redraw my neural network up here so that I've got an input of 1, and then an input of x1, x2, and so on, and that has a weight, a b associated with it, which I can call w1, for example, then x1 has a weight associated with it, and x2 has a weight associated with it, and all these things get summed up together, and that goes into our activation function, A, and then that goes out to Y, then we can see that by making a constant input here, then we can make this, we can sort of linearize. Before we had this affine way to think of things, and now we have a linear way of thinking things by fixing an input to be a constant. Then that allows the bias to be incorporated into the weight vector. And so, so all I really need to do is find a weight vector that corresponds to this separator between these two. And so, so that's what we are trying to do. So I use the term affine there. So affine just means linear plus bias. And so if y is equal to ax plus b, that's affine. And if you set b equal to 0, then that is linear. And so by treating this b as a weight, then I basically can say, well, y is equal to ab times x1, and then that turns an affine problem into a linear problem, because now my inputs include a constant component. So that's, yeah, you see the word affine shows up, yeah, great. Okay, so that is what we're trying to do for this perceptron. And so we are trying to find a feature vector that characterizes American cars. And so this perceptron is just a binary classifier. And so that, and so in order to do that, that's where so-called supervised learning comes into play, where we can provide a bunch of a data set, which is going to be, you know, it's going to, we'll have any particular set of features that we're interested in. So, you know, x1, x2, and so on, and as our kind of inputs, and we pair those up with classes. And so we can say, then we've got some class that, you know, C, I'll just call it C, and this is our, you know, which, this, say C is in 0 or 1, where 1 means that it's an American car, and 0 means that it's an import. And then these inputs are like the car size and speed. And so we feed those things in, and we then use a relatively simple method to tune our weights over time. And so we'll just say, 1, let's start with random weights, W, and here I am including bias in weights, as I was showing you before, just to keep this easy, because that way we can train both the weights and the bias. And then step 2, then I can do a simple iteration where I just say that for every weight, the next value of the weight is just equal to the previous value of the weight, plus, and then I'll just say, well, it's the weight vector times, and in this case, this is going to be input J. So I might view this as input J. So you've got a bunch of data points, and this is the Jth data point. And then I've got my desired, so this is effectively the guess, the neuron's guess at the class. And so this is for a linear regression is what I'm writing here. So imagine if the activation function, so this is, I'm just trying to generalizing here, but you could imagine, you know, putting different activation functions in here as well, but you basically calculate the fit of your feature vector to the input, and you compare that with what you're expecting. So you've got your desired output. So I'll say yj. So this is output j. So both of these are data, and this here is calculated. And then you can say multiply that by the ith component, because I'm worried about the ith weight. So I can multiply this by the ith component of the jth input vector, of the jth data point. And so this gives you a kind, and then you can repeat this for each xj, yj pair. And so this is a kind of simple form of you're taking a difference and you're scaling it in the right direction so that you push weights to move things around. And so I guess I said this is for all I as well. And so in this simple algorithm, there you can show that this will converge if the data are linearly separable. And so there's a question about step size. And so this particular algorithm, I see what is the input. So I view these are my inputs. And so the input is like, for this particular car, what is its size and what is its speed? And what type of car is it? It's an American car. So the output is American car, 1. The input is size and speed. It's this big and it's this fast. And we don't have to worry about a step size for this particular algorithm, because if your data, if you can assume that your data really are linearly separable, then this cute little algorithm here ends up converging to a separatrix. It converts to something that can separate the two spaces in half. And so, so for this restricted problem, this is a very simple training algorithm that can do it. But the intuition that we might need more generic training algorithms for more generic problems, and those are going to have things like step size, is a good one, and that's where we're going to get into next. But I just want to say, for this simple problem, I guess I should say this is for a binary classification task. On, I guess, linearly separable data. For linearly separable data, and you only have 2 classes, then this simple algorithm will work. Start with the random weights, and then you run down this algorithm here. And but then, I don't need you to focus too much on the details of this particular algorithm, but just the idea that effectively we are starting with a random way to separate this space, evaluating if that's a good way to separate this space, and then from there gradually moving toward what hopefully is a good way to separate the space, and we converge on something like the orange line, or something that at least approximates the orange line. And then ultimately what we're really doing is, again, a generalized linear model where we have come up with the right regression coefficients to best fit the relationship between these 2 inputs, car size and speed, and a transformed version of this classifier of well, 1 if you're an American car and 0 if you're an import. So that's really all that you're doing in the binary classification problem, is just a logistic regression, or a binary logistic regression in this kind of generalized linear model. But that's kind of the geometric interpretation of what's going on with this. How can we tell whether data is linear separable? Do we? So yeah, that's a good question. So for you make that, so yeah, you could plot your data and you'd say, yeah, it looks like it's linearly separable, in which case then you do this fitting. That's a little bit like, again, if we really think of a single neuron doing this task as being identical to doing a regression problem, then your question really is, how do I know that I can fit a linear model to this? And so the way you do that in a data science perspective is you'd maybe transform your data, and then you would start fitting linear models to it. And then you'd say, are the, what do the residuals look like? Those sorts of things. And so that's really what we're saying here is, does the relationship look linear? So for the activation function that we have chosen, then do we get kind of a linear relationship? And that's basically what we're saying here. And so it does take either some faith that your data will be linearly separable, or some prior knowledge where you plotted them all out and then you said they're linearly separable. But given that they're linearly separable, you'll converge to this. And then, yeah, so the higher dimension stuff, then, yeah, you might have to, I mean, this gets into kind of data science-y stuff, that how do you visualize these relationships and higher dimensions? Yeah, so again, all of, I mean, really what it's going to come down to is, this finds you the best binary classifier, and then really what you need to ask afterwards is, how good of the fit is it? Because this classifier, if you have something that isn't linearly separable, and so if you've got something ugly where you've got a bunch of data that is out here and another bunch of data that is in here, and you don't have a way to draw a straight line into separating those, then you're going to be able to evaluate the fit of your model. And then, and if it's a really terrible fit, then maybe you shouldn't have used this particular classifier to split them up into these two things. But the way this classifier is built is sort of saying, let's start with the simplest problem. The simplest problem is that we can just use a plane to cut them in two. And if we can use a plane, then can we numerically find that plane? And it turns out that we can with a relatively simple algorithm. And so where we're going to go next with this is like, okay, so that's great, but again, a single layer perceptron, so a binary classifier, is really just a generalized linear model with the right activation function. And so we say, well, how do we build more interesting and more sophisticated models? And so we're going to move then to something that looks more like, actually, so right now we don't have a network. So in other words, where is the network? And so where we go next is filling in that gap and start saying, all right, what happens when we start combining these neurons together? Do we have to combine these neurons together? So if you combine them together in a particular way, are there ways in which we can reduce them to simpler forms? Or are we stuck with the more complicated form? What type of activation functions are amenable for these? Do we need feedbacks, and so on and so forth? And what can biology kind of teach us about these things too? So that's kind of where we're moving for now. But today I just was sort of wanting to focus on introducing the neuron and the basic binary classifier task as a conceptual model for what a neuron can do. So are there any questions about that? And that's kind of where I'm going to end it for today. About the score, our look. Oh, sorry, the scope. Gotcha. Yeah, so basically I'm talking about this basic, these neurons here. Then we'll talk about multi-layer perceptrons, which are still feed forward. That's kind of next. And then we will talk then about recurrent neural networks, and we'll talk about some things a little bit about like reservoir machines, for example. So I just want to get you to the point where you kind of can see a couple of different feed-forward topologies and a couple of different recurrent topologies, so that we can hopefully make a relationship to other things downstream, like cellular automata. And so, and then I will talk about spiking neural networks as well, at least a little bit, because it turns out the topology alone isn't like where all of the computation is happening. And so much of neural networks up until recently has been focused just on the network and not about the physiology of how these neurons work. And it turns out that spiking, you can get a lot more from spiking than you can from just a network. So, so that's basically, I think I've covered what, what it's going to be basically, I don't have about maybe 3 lectures covering neural networks before we move on to CAs. And so if you've already seen a lot of the neural network stuff, then it probably won't get interesting until we get into recurrent neural networks. But so if you already know what backpropagation is, that's probably going to be review. And then an AuTaps, somebody asked, is an AuTaps like an RNN? An AuTaps is a particular thing that you fit. Like that would be one connection within an RNN, a neuron that connects to itself. But you can also have neurons connect to neurons and eventually connect back to itself. And yes, I know that there's no documents on this, and so I will then populate. Because so much of this has just been kind of basic background, I haven't been working off of a set of papers, but I'll look back and see if I can find like something that's easy for me to export without like photocopying out of a textbook or something like that. So that I think was my issue the first time I came up with this, is most of it was just from memory. And so I wasn't working from something, but I would like to give you guys something that you can work from. So I'll kind of scour literature to see if I can find like a nice survey of neural networks or something like that. All right. Anything else? Yeah, so the term affine. So anybody else who wants to drop off right now, I'm just kind of answering questions. It's 4:22, so I understand about the time constraints. So there's this question about this term affine, and affine just is a relationship between inputs and outputs where you need a bias term. And so if you have a function y of x, if x is a vector, if you can represent that as some transformation A times, where this is a matrix, times X, if that's enough to represent that, then that's then that would be linear. But if you need an additional vector to add a bias or an offset, then that bias is what makes it a so-called affine relationship. So it's just a term that is slightly more general than linear. So any other questions? For the project, we use existing libraries and methods in Python or MATLAB. You have to build the algorithms from scratch. You can use existing algorithms for aspects. So it's like if you are implementing an algorithm that's new, I'd like you to build that yourself to sort of show to me that you know how it works. So that it's like the Feynman quote about not being able to understand it unless you're able to build it. But if you then need to set up baselines and things like that, then it's okay to if you're using a genetic algorithm as a baseline, then you can use the genetic algorithm that's already been implemented in Python. Or if you need to use a bunch of auxiliary functions, then those auxiliary functions are readily available and they're nothing that is specific to the algorithm you're trying to build. It's okay to use those auxiliary functions. So you don't have to write everything from scratch, but I at least want you to make an implementation of the nature-inspired meta-heuristic that you are focusing on, or the nature-inspired algorithm that you're focusing on, so that we can see that you really understand the internals of it. Does that answer your question? Okay. All right, anything else? All right. Okay, so in that case, I'm going to at least stop the recording.